about the quotient topology. The quotient topology is the one where you take your original topological space and create a new topological space by gluing together parts of it. And the standard example is, say, the closed interval 0 to 1, or really any closed interval, but you might as well use 0 to 1. And by means of some sort of gluing operation, if you stick the two ends together, it becomes something that looks like a circle. You wrap it around and glue the first point to the last point. So this is, we typically call this S1, the circle. The quotient topology describes a certain way about how exactly do you define which are the open sets over here in terms of the open sets that you started with. And basically it's like, well, because this is a wrapping up, the open sets over here are like little open intervals. And when you wrap those up, a typical open interval is like a little one of these. And when you wrap that around the circle, it's going to end up looking, maybe like this one over here, something like that. But the quotient topology, which we will talk about the real definition today, it tells you exactly how you get these open sets over here in terms of these open sets over here. All right, it's a way of taking the topology you're using on this space and creating a topology on this space. This is a standard example. Other examples that we drew pictures with last time were things like you can start with a unit square and turn it into a cylinder or even a torus. That's the most interesting one, perhaps. By gluing together, in this case, you would glue together the two opposite sides of the square. So glue together the two vertical sides and then also glue together the two horizontal sides. And actually, there's a way, I don't think I did this last time, but diagrams like that we often draw this way. So these arrows mean like this has one arrow and this has one arrow, and that means those two get glued together. And then the two arrow ones, it's not like this is twice as much as that. It's just there are two arrows on this one to tell you that that's meant to match up with this one. That makes a torus. All right. You can get other kinds of things, like what if I did instead, you can imagine, what if I just sort of glued together in a different way? How about like this? This is a little strange, maybe. So this means I glue this side to that side, and I put the arrows in the direction of the arrows just kind of tells you what direction to glue them in. So here it means it's as if you had this as a piece of paper and you have like these two sides, and you just kind of bring them together, right? Their two ends are already together, but the rest of the line you glue together. And then the other two sides you also glue those two together. Can anybody say what kind of a shape do you end up with if you did that? Can you imagine in your mind? In real life, if you did this? Yeah? Triangle. There is something triangular about it, but I think it has some, maybe I could try to draw, I'm not a great drawer, but if I were to first glue the two double arrows together, so imagine that like these two guys are still here, they have not been connected yet, but the other two are connected. I think if I was really doing this in real life, when I glue those two together, at least this part of it looks kind of like a cone now, right? Like a dunce cap sort of a shape. Sort of, this kind of a thing. Although these guys, I mean, once you stick these two lines together, then these two lines also sort of naturally will stick together. I think really you get sort of a cone up there and also like a cone in the bottom, right? which is vaguely triangular, but I would say maybe I shouldn't even draw these guys. It's more like that kind of a thing. I hope you can see that in your mind. Topologically speaking, if you ignore the fact that it's pointy on the other two ends, this is like S2, the sphere. Right? Usually we will ignore the pointiness of the ends. Topologically speaking, this is like a sphere, where this cone here is like the northern hemisphere. That's like the equator, and that's like the southern hemisphere. All right. Yeah, you can think about move these arrows around however you like, and think about what kind of a shape would it produce. You can a little something to play around with if you're into that kind of a thing. This one is the most interesting to me. I remember when I was a kid. I used to like playing the video games when I was a kid, and this is the topology of the screen in the classic arcade game Asteroids, where you fly around, and when you leave the screen this way, you can come back this way, and also when you leave the top of the screen, you can come back in the bottom. That means the Asteroids guy is somehow flying around on the surface of, like, topologically speaking, a torus kind of a thing. I was also a big fan of the old Final Fantasy games. I was in the prime audience when Final Fantasy for the Super Nintendo came out. It was pretty awesome. But that's a game where you like walk around on a map of the world. But in Final Fantasy IV, which was called Final Fantasy II at the time, that in the world map, it was like this. If you walk off this side, you come back that side. And if you walk off the top, you come back on the bottom. That means actually the planet that they live on is not a sphere. It's a torus type shape, which I always thought was kind of funny. And in that game, actually, they go to the moon and they like look back at the Earth, and it looks like a sphere. I thought, come on, guys, don't make no sense. Anyway, if you actually lived on a torus-shaped planet, the day and night would be weird. Somehow, the entire planet is always daytime. In the Final Fantasy games, at least. Okay. I was also a big fan of Civilization, which is a bit more realistic game, and you will know if you played Civilization. Actually, on the map in that one, you can go off the right and come back to left, which is, I suppose, realistic. You can go around the Earth eastward and you come back westward, but you can't. You just in Civilization, they just don't allow you to go off the top. Certainly, you do not go off the top and come back on the bottom, because that's unrealistic in the real world. You cannot go to the North Pole and then just appear at the South Pole in the real world. All right. Anyway, let's talk some details about this. As an example, I want to focus on this example just because it's like the simplest, and then we'll talk about some other more interesting ones here. Generally speaking, you start with X, which is kind of like your original space, and then you glue it together in some way. You glue parts to obtain A. This is just the language, the notation that they typically use in the book. X means the original thing, and then A is the thing which is obtained after you stick bits of it together. And the way that exactly how do you describe the gluing part? So this is my X, which in this example is 0 to 1, and it turns into the circle, which is what the A is, right? How exactly do you describe how the gluing works? You use a function. So this gluing is described by a function. And that function is always called P. It goes from X to A, and it's called the quotient map. In topology, the word map is often used to mean function, or sometimes people say mapping, the quotient mapping. It just means it's a function. All right. This is a little confusing when I'm talking to people and they ask me what kind of math I do, and I say topology, and they don't know what, they've never heard that word before, and they say, oh, is that about maps? And they say that because they think I said topography, which is about maps. And I say, no, it's not about maps. But deep down in my heart, I'm conflicted, because actually we use the word map all the time in topology. It means function. It doesn't mean a map on paper, which people who study topography are interested on maps on paper. Anyway, this is called the quotient map, the P. So in this example, what is the P? The P is actually usually inconvenient to write down the P as a formula. What specifically is the formula which takes this line and wraps it around into a circle like this? Usually we don't do this because this is it's a pain to write the formula, but in this example, so for this interval 0 to 1 mapping into the circle, we can use P. So this is my function P, right? Its domain is the interval 0 to 1, and its codomain is the circle. I can define it this way. If you think of the interval 0 to 1 as like little moments of time, something like that, I can write the formula this way. And you'll see immediately why we usually don't do this. Cosine of 2 pi t, comma, sine of 2 pi t. What this is it's a parameterization of the unit circle using time, which goes from 0 to 1. Usually if I was going to, this is something you do in Calc 3. If I was going to parameterize a circle, usually I would use the domain interval, I would use like from 0 to 2 pi. Then you could just do cosine t, comma, sine t. But since I'm specifically trying to use 0 to 1, I have to put these 2 pi's in here, all right? We almost are never going to actually write formulas like this, and probably you did not expect me to break out the sines and cosines in this class, right? This is not the typical thing that topologists like to do. So from a topological point of view, really all that matters is that there is such a function that does this, and almost never is it important to actually write down the formula for what the function is. But just for once in our life, you can write down the formula if you want to. So I will say, usually we won't write formulas just because it's a pain to write the formula, and actually it ends up not really mattering much anyway. We're going to talk later on today, maybe if we get to it, about there's another way of describing the quotient topology without using functions like this, which is a little more convenient. But we're going to go with this for now. All right. You can do a quotient topology whenever you have a function like this. Now, you might wonder about, is this always going to work? Like no matter what the P is, can I do something which gives a real quotient topology? And the answer is yes, you can use any function that you like. It doesn't even have to be continuous or anything like that, although this one is. The only requirement is that P has to be a surjection. It has to be onto. That's because you want to be sure that what you get is actually the whole circle. If P is not onto, maybe P, like, if I used a different function, which say only hit that part of the circle, then really I'm not getting the circle. I'm only getting this, which is basically the same as the interval that I started with. So the requirement is, in order to be a real quotient map, the P has to be a surjection, or it has to be onto. So P must be onto, or maybe, I think our book prefers to use the word surjective, or P must be a surjection. So I hope you're comfortable with that language too. Surjective means onto, all right? If P is not onto, then you don't actually get the thing that you're trying to get. You get some subset of it, which is not what we're talking about. All right, let me tell you the real definition then. So this is the basic setup. The definition has to tell me, additionally, which I haven't said yet, how do you tell what an open set is over here? It's based on what the open set's over here somehow, but you use the function to tell. Here, anyway, here's the definition of the quotient topology, and then we'll just do some examples. So, okay, for a topological space, X and any set A. The A is not a subset of X. It's just a completely different thing. Like in that case, I was talking about an interval and then a circle. So it's really, the A could be quite different from X. Anyway, for a topological space X and any set A with a surjection, that is an onto function, P going X to A. This creates a topology on A called the quotient topology. And it's defined by, so I have to tell you what makes a set of A open in terms of the quotient topology. So U is open in A. If and only if, here's the real definition. How do you tell if a set in the A, that is the circle, is open? It is defined to be open if and only if the pre-image P inverse of U is open in X. All right. So you take a set in the A, which is like the circle, the quotient. It is defined to be open when, if you bring that set back to the domain, it makes an open set in the domain. This is the definition of the quotient topology. Yes?
Is it wrong to assume that any open set in X gets put into the function that output of that is?
Yeah, maybe you were expecting me to say, how do you tell if it's open in A? It is if you start with an open set and then you push it forwards, rather than I said instead you pull it backwards. It turns out, I believe the definition is different if instead you say the open sets are ones which are images of open sets from X. This is a much more convenient, and actually I don't know if you get worried when I start talking about pre-image of a set. Actually, the pre-image is much easier to work with, as we'll see, than the forwards image of a set in topology is often weird, but the pre-image is much nicer. So you will learn to love the pre-image. All right. Let's look at some examples. Let's just look at the circle. That interval and circle example. So in this case, this is my X over here. X equals 0, 1. I should say, you have to view X itself as a topological space. So I'm going to view X as 0, 1 with the subspace topology from R, right? That's the most ordinary topology you can put on the closed interval from 0 to 1. And then I have my function P, and it turns everything into this set A, which is S1. Now, actually, I'm not going to tell you what the topology on A is. The topology on A is the one that you get from X by doing the quotient topology, all right? This is A equals S1, all right? Now, I sort of labeled this point here so that what I mean by putting a dot right there is that this function here, it brings those 2 points and puts them both there. And then all of these other points just sort of get stretched around the circle. All right, that's how the parameterization of S1 works in R2. Okay, so I'm gonna let's draw some pictures of sets in the S1 and ask, are they open using the quotient topology? So I'm going to just be redrawing this set over and over again. What if I have, say, a little sort of thing that looks like an open interval? Maybe I'll use the empty circles kind of thing. A little set like that, right? Is that an open set? So this is my U. Is that an open set in the quotient topology? You have to pull it back to X. This pre-image sometimes is called the pullback. All right, P goes that way, but I'm going to bring this set U back to the interval and then ask myself, what does it look like when I bring it back to the interval? The way that this parameterization works, remember, is that you know, these two endpoints end up at this point, and the rest of these points go around the circle counterclockwise. That's how that, if you use that cosine comma sine parameterization, that's how these points go. So for example, the point right in the middle, can anybody say, according to this function p, where does that point end up over here? You wrap the interval around counterclockwise. So the point in the middle over there ends up, what would you say? Yeah.
That'd just be like middle left.
Yeah, it would be the leftmost point on the circle over here. So that point, that green point, ends up at that green point over there. All right. So, and maybe this will tell you, where does this u end up when you pull it back? That is, I'm looking for all the points which go into u. I think it would be a blue set sort of over here, right? Because this little interval here is happening kind of between the starting point and the green dot, right? So this u pulls back to a set that looks like this. And it lacks its endpoints. That's just how the function works. The function, if those endpoints were there, then the endpoints would be there when you pulled it back, but they're not. All right? And what do you say? After I pulled it back, is this set over here open in X, or is it not open? You have to think this is the interval with the subspace topology from R. Is that a open set over here? I would say this is open in R, right? Because it's a little open interval. So this is open in X. That set, this is P inverse of U, right? That's what happens when you bring U back over there. It is open in X, so U is open in A. This is how you tell if something is open or not in the quotient topology. You bring it back to X and then see if it was open over there. All right? So that's what an open set over here looks like. What if instead, here's another example. How about I chose something like a half closed interval over here? So that's like the old U, but it includes one of its endpoints now. When I pull that back over here, it becomes, it's very similar, only it's going to include one of its endpoints. And actually, since the parameterization goes counterclockwise here, this includes the first endpoint, but not the second one, right? So when I pull it back, it looks like it includes the left endpoint, but not the one on the right. Something like that, where the middle point is like here again. All right, so that's my P inverse of U. And that is not open in the standard topology from R, right? Which is what I'm using in the subspace topology. That is not open in X. So this set over here, U, this one, is not open in A. All right. Basically, the open sets in this circle, they look like little open intervals. It's because what determines if they're open or not over here is basically, do they look open or not when you unroll them over there? And it's basically just things that look like little open intervals, all right? We do get an interesting example if you look at a set which bridges this point. Let's look at a little interval which goes across that point, because something weird is going to happen then when you pull it back to the original space. So let's try one like that. I beautified my circle that time. What if my set goes, let's make it something like an open interval, but going through that point. Now, if you ask me, I would like for this set to still count as open, just because it still looks like a little open interval. The fact that it happened to go through that special point shouldn't really matter, at least in my opinion. On the circle, I don't really want for the special point to make any difference, exactly where that big dot is. Anyway, here's the interval over here. And I'll put the center dot in there just for reference. Anybody want to say, what are you going to get when you take the pre-image of that if this set over here is my U, I hope you don't mind me calling it U every time. What does it look like when you pull it back to the domain this time? I want all of the points from over here, which end up in the blue zone over here. Yeah?
You take like basically two intervals where they both touch like the left and the right.
Yeah. So he says two intervals which sort of touch the two ends of this. Yeah. So, and actually it would include that point, and it also would include that point, and it'd be some kind of little interval on either side. And then what about the other end of say this interval? I think would be omitted here, just because like this point and this point are missing in the original set. So it looks something like this. Yeah, great. This is what, you know, those two things together is P inverse of U. Excellent. A little strange, I suppose. Anyway, is that an open set in the subspace topology of the interval? Well, it's a union of two things, but if they're both individually open, then that's okay. Is this an open set in the subspace topology? I believe it is. This is similar to things you were talking about on the homework. Remember, the subspace topology means an open set from R that's been intersected with the interval. And you can make this as an open set from R that gets intersected with the interval. That would be, you know, if I took something like that, is an ordinary open set from R intersected with the interval. So those two guys together, this one is open in 0, 1 with the subspace topology. Those other examples, we didn't really care about the subspace topology, but it makes a difference in this one particular example. All right. And so that means this original set over here, U, is open in S1. All right. Really, it is a fact. The open intervals on the circle, or the open sets on the circle using the quotient topology, are just things that look like little open intervals. And it doesn't matter if they go across the base point or not. All right. Actually, this is what you get here. So S1 using the quotient topology from 0, 1 actually is the same as the subspace topology from R2, right? Those little intervals that you get, actually those are the same kinds of sets that you would get if you considered this as a subspace of R2. Because remember, the open sets in that case would be open balls from R2 intersected with the circle, and that's what you would get if you intersect the circle with some kind of open ball. All right, this is the quotient topology. Any questions about that example? What I would like to do as our sort of only proof of the day is I would like to demonstrate. So this is our theorem. Theorem for the day is this definition here. This is the definition of the quotient topology, right? There is something to say about, are you sure that this gives you a real topology? What it takes, this might be a good little review for the test. I hope you remember what it takes to be an actual topology. You can't just say anything you want is a topology. A topology has to satisfy the three properties. There's one is the empty set, and the whole thing have to be open. Also the finite intersections property and the unions property. So I want to try to demonstrate that for the quotient topology. So I'm going to say for the standard setup of a quotient topology situation is when you have a function x to a onto. The quotient topology on A is a topology. That's the theorem. We have to verify the three properties that makes it a real topology, an actual honest-to-goodness topology. All right? Those are that well, let's just do it. The first property is that empty set and A are open, right? Usually I would say X there, but I'm trying to show that A becomes a real topological space. X we assume is a topological space. We're trying to show that A is now a topological space. So the empty set and also the whole space, which is A, that's the space we're talking about, have to be open. So let's talk about empty set first. You know, the question is empty set open in A? That is equivalent. What does it mean to be open in A? According to the definition of the quotient topology, that means that P, the preimage of that set, is open. So this question here is empty set open in A is the same as asking is P inverse empty set open in X, right? So can anybody say, any masters of set theory, what is a P inverse of the empty set? The pullback, the pre-image of the empty set? The magical facts from set theory?
I feel like it's empty set.
I think it's the empty set. Yeah, you just have to remember what this means. This means what are all of the points in the domain so that when you do P to them, it ends up in the empty set. And the answer is, well, there is nothing in the empty set, so no points end up in the empty set. So the preimage of the empty set is the empty set. This is a basic fact about all, you know, any function has this property. Anyway, the question I'm trying to answer is this open in X? So this is the empty set. Is that an open set in X? Yes, it is, because X is a topological space, and that's one of the properties of any topological space. So this is open in X. This is because, I'll just say, since X is a topological space, automatically empty set and X are open, right? That's the first rule of Fight Club in a topological space. All right, so this is open in X, so that means empty set is open in A, right? Because when you pull it back, it goes back to something which is open in X. Great. All right, that was half of this one. Now that we see the basic format, I think the other half will be easy. What about A? So all of this was about the empty set. What about A? I got to do the same thing. Is A open in A is the question. How we evaluate that would be this. P inverse of A, is that open in X or not? Any thoughts about, you know, in the previously it was fairly easy because P inverse of the empty set is the empty set. Can we say what that is? P inverse of A. Remember our scenario is we have X, you know, whatever X is, and then P carries it over to A. Yeah?
Is it because P's onto that it's equal to X?
Yes, this equals X, and that's because P is onto. And actually, this is the only part of the whole thing where P is required, where the onto makes a difference. So this equals X, since P is onto. That's the only step, I believe. I don't think we use this elsewhere in the proof. Because P is onto, it means when you pull back A, you get the entire set X. All right? And is that open? Is X open in X? Yes, it is, because it's a topological space. So P inverse of A is X. So that means P inverse of A is open in X. So A is open in A. That's the quotient topology. All right. This is the easy part of the proof. Usually, I don't know if you feel the same way. I usually feel when I'm showing something as a topology, the first property is like the easiest. The other two are a little bit more interesting, although the other two are not such a big deal in this case. But anyway, that's the first one. All right, let's do the second one, the finite intersections property. For the test, I hope you remember these three properties. The finite intersections. All right, for this property, I have to say, I take, you know, U1, etc., UN open in A, and then I want to show that the intersection I equals 1 to N, UI, is open in A. Right? That's the idea. if everything is going well for you in life, you should be able to work this out just by kind of writing out definitions. So I'm going to say, since these are open in A, what does that mean? It means the preimage is open in X. That's the definition of open in A. So I'm going to say, since UI is open in A, then P inverse of UI is open in X. That's what it means to be open in A. So the preimage is open in X. All right. And what I want to end up with is the intersection of all of these things. So I think it might be appropriate to just take the intersection of all of these sets. So this is open in X. So the intersection, I equals 1 to n, P inverse UI is open in X. This is the finite intersections property for X, right? X is a topological space. So if I have finitely many open in X, I can intersect them together, and the result is also open in X. So this is the finite intersections property in X, right? You may be worried I'm using what I want to prove. I'm not. We're trying to prove the finite intersections property for A, right? But we assume already that X is a topological space, so we can use the finite intersections property in X. All right? And is that what we wanted? I mean, this and this, they're close. Actually, what we want to show is that the preimage of that intersection is open. What we've shown is that the intersection of all the preimages. But this is another sort of random fact from set theory, I will just say. But this intersection, P inverse UI, this is actually the same as P inverse of intersection UI. This is a set theory fact that you probably showed in your discrete math class and forgot about. This is the kind of thing that I forget about too, to be honest. You look it up if you're ever concerned, or if you're feeling a little, if you're feeling lucky, you just say it, even if you aren't sure if it's true or not. That's how people do it on the test. You just say it anyway and hope that it's right. Okay, this really is true though. This means, if you think of it as sets, this is all the points so that when you plug them into P, they end up in UI. And what this is all the points so that when you plug them into P, they end up in all the UIs. It's the same set, all right? I don't think I said it very well when I just said it. Anyway, what we've demonstrated so far is that this is open in X. That's what I already said, that one there is open in X. So that means this is open in X. So P inverse intersect I equal 1 to n UI is open in X. And so the definition of the quotient topology says that's what it means for this one to be open in Y. In A. All right. The end of the finite intersections property. The finite intersections works in A just because the same thing works in X. All right. Would you mind if I just say the unions property is the same idea? It really is. You could just copy step by step. Every time, instead of using intersections, you use unions. It goes exactly the same way. All right. The only difference, of course, is that it's not a finite union anymore that you start with, but by the time you bring it back to X, even if it's an infinite union, you're going to use the infinite unions property from X. So everything is going to work just exactly the same as it did before. All right. I'm going to leave it at that, just because I wanted to say another thing before we leave today. Anybody got thoughts about the proof here? This is just to justify why this quotient topology concept even works at all. It does make a real topology. All right. Great. in our remaining 9 minutes or so, I want to try to explain how to do all of this without using specific functions. Like I said, we don't usually want to write down specifically what the function is because it's usually a pain to do. Like it's very difficult, actually. I wouldn't want to do this for the torus, for example, obtained by gluing like this. And this becomes the torus, right? Anybody happen to know a parameterization of the torus in R3? The answer is no. At least I don't. This is not easy to write down a parameterization for that. Is it easier if you use cylindrical coordinates? Maybe. I don't even know. I don't know how I would do this if I had to do it. I don't want to do it. I'm a topologist, which means I usually don't actually care about the functions. Let me just say, P as a function is complicated and not really worth it. Like you don't actually, for the most part, you don't care about what the formula for the function P is. It is easier to express using equivalence relations. So this is what I'll give you a little preview today. We'll talk about this more next time. Easier to express using equivalence relations. I hope everybody remembers the definition of an equivalence relation is a relation which is reflexive, symmetric, and transitive. Although we're not really going to get into the weeds with precisely what counts as an equivalence relation or not. The way that I want you to think about an equivalence relation is just in X, we imagine some points are equivalent to some others. The standard example that we've been talking about all day is, the closed interval like this. If I look at that and I just imagine, I'm going to pretend like the point on the left end is the same point as the point on the right end. That's really what you mean when you say I'm going to glue the ends together. It means I'm going to just imagine like those 2 points are actually the same point. So this is another way of thinking about it, not so much as a function, but as an equivalence where in this example, so from here, 0, 1, we are regarding 0 to be, in our book, the equivalence relation, they usually use this tilde, like operation or something, as a relation. We're regarding 0 and 1 basically to be as if they were the same point. And then all the other points are not the same as anything else. All the other points are still their own point. But the 2 endpoints, we regard them as the same. This is much, in my opinion, a lot closer just sort of to the notion that we're going for, which is we are sort of imagining that we are gluing them together, right? We are regarding 0 and 1 as being equivalent to one another. And I will say no other points are equivalent. I'm not trying to glue anything else to anything else. No other points are equivalent. All right, only the 2 endpoints are being identified. That's the terminology that's used sometimes. We are identifying the 2 points. That is making them the same as each other. All right. So here's some notation that we use here. So let's say that if X is a topological space that also has some kind of equivalence relation, that is, you are imagining some of the points to be the same as each other. If X is a topological space with some equivalence relation, I'm going to say let X star be the set of equivalence classes. And I hope you remember what that means. Equivalence classes would just be each point is in the same equivalence class as all the other points that it's equivalent with. All right? So the set of equivalence classes is the X star. In our favorite example here, this to the circle. So if this is x, right, here, x star consists of, what do the equivalence classes look like? Well, I said 0 and 1 are equivalent to one another. So one of the classes looks like this, 0 and 1. That's one equivalence class, because these are 2 points which I am regarding as the same as one another. And then all the other equivalence classes would just be individual numbers. All the other numbers, they live in their own class by themselves. They are not equivalent to anything else. So it consists of that class plus all classes that just look like x when x is not 0 or 1, right? Every point by itself is still a class by itself because it's not being regarded as equivalent to anything else. The only kind of interesting equivalence class is the 2 points on the end, all right? So that's what x star would be in that example. And then, I will just say this, leave us with this, then the quotient map, the P, is just like this. X goes to x star, where on a point, P of a specific point equals, I will write it that way. That means the class, the equivalence class of that point. All right. In our favorite example, what does this function look like? Well, every individual number is just in its own class. So most of the numbers just go to themselves, but the numbers 0 and 1 are mapped both to the same point over here because they go to the same equivalence class. All right. This is a way that you can create your quotient map P without ever writing down a formula like with sines and cosines or whatever. P is just defined to be the function which sends everything to its equivalence class. All right. Maybe we'll leave it at that then. We'll do some more examples using this type of quotient with the equivalences